Hi students, welcome back. Today we are going to solve the maximum depth of binary tree problem. Let's look at the problem statement. The problem statement says we are given root of a binary tree and we have to return its maximum depth. Okay, maximum depth meaning how is maximum depth defined? Maximum depth is the number of nodes along the longest path from root node down to the farthest leaf node. So number of nodes from root node to the leaf node, farthest leaf node is called the maximum depth. Maximum depth is nothing but the height of the tree as well. Okay, let's look at an example. So in this example, the maximum depth nodes are 15 and 7. So the distance from root node to them is uh, either 320 15 or 327. Both of them has number of nodes as 3, which is why our output is 3. Okay. Now if we look at another example, this one has just 2 nodes, so single path. So the number of nodes is obviously 2. So before we go to solving this problem, let's look at some simple concepts of trees. So here if you see the highlighted nodes 9, 15 and 7 has no children. Okay. So their next pointers will point to null. Okay. Such nodes are called leaf nodes. Okay. And if you look at the node with blue background, which is 3, this is root. This is root because it doesn't have any parent. Okay, so root of a tree doesn't have any parent and leaf nodes doesn't have children. Okay, so there are two concepts to the trees in terms of height. So one is called the height. Okay, the other one is called the depth. Okay, depth is the distance from root. Distance from root to this node. Okay, height is the how far is it from the leaf node. So distance from leaf node. From leaf node. Okay, and this depth and height, they can be measured in terms of number of nodes or number of edges. Number of nodes is the most common one, but number of edges is the most common one, but number of nodes is also used, and that is what we were asked in this question. Okay, so let's see how height or a depth works for let's say node 9. Now if we do it in terms of number of nodes, height is for 9 distance from leaf node. There are no leaf nodes. There is this node itself, so height would be 1. Depth is distance from root. Okay, so there are 2 nodes in this path from root, so depth is 2. Now the same thing, if you look at in terms of edges, it would be -1 basically. Okay, height would be 0 because there are no edges and it is a leaf node, and depth would be 1 because it is only this path. Okay, now if you look at the same thing for node 20, now let's look at only in terms of number of nodes. Okay, height would be distance from leaf node. 7 is a leaf node, so there are 2 nodes, so height would be 2. Depth would be distance from root, which would be 2. Okay, now for 15, height would be 1 because it's a leaf node, and depth would be again number of nodes till the root, which is why it would be 3. Okay, so that is how height and depth are defined. Okay, now that we know height and depth, let's look at how we can solve this problem. Let's say this is our example tree. Now height of a tree, height of a node can be defined as max of height of its left node plus height of its right node plus 1. Okay, so what we are saying is height of a node is nothing but max of left or right. So that means either left or right, whatever is has the maximum height plus 1. Okay, it's plus 1 because we have to add the current node. So this is how height is defined. Max depth is nothing but height. So if we find the height of a tree, we will get the max depth. Now let's use this formula to see how we get the height in this case. So to find the height of 3, we have to first find height of left and height of right. Height of left is a node with two children, null and null. Okay, so for them height is 0 because there are no nodes itself. For 9 it would be max of left and height left or right plus 1, so this would be 1. Similarly, to find height of right, we have to again go to the leftmost node. So this would be similar to 9, so height would be 1, and the rightmost node here height would be 1. Now height at 20 would be max of left or right, which is 1 plus 1. So height here would be 2. Height at 3 would be max of 1 and 2, which is 2 plus 1. So height would be 3. So this will give us max depth answer. Okay. This is a recursive way. This is very simple. You just find the height of left tree, height of right tree, take the maximum in that and add 1 to it to account for the current node. Now there is another way using the tree traversals. So height, so this max depth or height is nothing but number of levels in this tree. If you look at this tree, it basically has 3 levels. Okay, level 1, level 2 and level 3. Okay, so if we can figure out the number of levels in the tree, then we will know the answer to the height as well. So we will find this using another data structure, a queue data structure. We will traverse the tree and then we will figure out the levels. So initially, okay, let's number this 1, 2, 3 so that it will be easy to represent in the code. So this is 1. Okay, so initially we are at level 1 and let's add the root node to the tree. So Q has 3. Okay, so at every iteration, what we will do is we will pop out all the elements in the queue and we will add all its children to the queue, which means at any point this queue will have all the nodes in that level. So now if we do it for a second level, so at this point level also will become 2. So our current nodes, we popped out 3. Okay, we popped out 3. Now we will add all its children to the queue, which is 9 and 20. Okay, now we will continue the processing. Now we are at level 3. Now our current nodes would be, we pop out all the children in the queue, not just one. Okay, so that means both 9 and 20 will come out. Okay, and we add children of both 9 and 20 to the queue. 9 doesn't have any children, 20 has 2 children, 15 and 7. We add them to the queue. Okay, now at the next level, it would be, we pop out 15 and 7. Okay, 15 and 7 doesn't have children, so there is nothing more to process. Next time when you come, the queue is empty, so we don't have anything to do. So we will finish the traversal. So this one correction here, we have to start with 0. So this becomes 1, 2 and 3. So this would be our answer as well. Okay. Now if you see at any point our tree was having the number of nodes in that level. For example, initially it had only 3, next it had 9 and 20, next it had 15 and 7. So we are basically storing all the nodes in that level in a queue and processing them together. And in the process we are also finding the height. Okay, so this kind of traversal where you traverse all the nodes in a level is called the level order traversal. Okay, so let's solve both these methods using code and that would give you even better understanding. Okay, let's head to LeetCode. Okay, let's reset this first. Okay, now The recursive solution is if root itself is null, okay, the height is 0. So we are returning 0. Otherwise, height is 1 plus max of root dot left, comma, okay, 1 plus max depth of root dot left, comma, max depth of root dot right. We find the max of left or right and add 1 to it. Okay. So this got accepted. Now if you see the time complexity of it, we are traversing all the nodes in the tree, so it would be order of n. Similarly, space complexity would also be order of n because of the stack which gets preserved. Okay, so the recursive solution is pretty simple. If it's null, it's 0. Otherwise, it is 1 plus max of either the left depth or the right depth. Now let's look at the iterative solution which we have seen. So even in this case, if it is null, we have to return 0. But otherwise, we have to define a queue data structure to hold the number of uh, nodes at a level. Okay. So in Java, linked list implements queue. We can use that. Okay. And to start with, we will add root to the queue and initialize a level variable to 0. So while this queue is not empty, it's not empty. What we do? We process all the children in the queue. Okay, all the nodes in the queue. So to figure out how many nodes we have to pop, let's define a size variable. And for all the elements in the queue, which means all the elements within the size range, okay, we pop out the element, okay, and we add its children. So we will add its children only if they exist. That means if they are not equal to null, then we add node dot left. Okay, we do the similar thing for right. If node dot right is not equal to 0, not equal to null, we add node dot right. So we are basically with this variable figuring out the number of elements in that level, popping all those elements and adding all its children if they exist to the queue. Okay, and once we are done processing, we have to increment our level variable. Okay, so if we return the level, that is nothing but max depth. Okay, so again here time and space complexity would be order of n because we are touching every node in the queue, and for space we are defining a data structure here, which is why though there is no recursive stack here, it will still take order of n space. At any point, the maximum nodes at a level would be order of n by 2 actually. So it will take less space than the earlier one, but constants we don't consider in the complexity, so it's still order of n. Okay, so that's all we have for this. Hope you understood the different definitions of binary trees and how to solve this in two different ways. Do practice. Only practice improves your coding skills. Happy coding. If you have any questions, do leave a comment. Please like, share and subscribe. Thank you.